Hello, my name is Sabo Ibrahimi and I'm the member of Pattern Recognition Lab in the Ferdowsi University of Mashhad. Today we want to discuss about RMS voltage. Hope you find this video helpful. We will start with an overview of RMS voltage and its significance, followed by its applications, calculation method, and the relationship between RMS, peak and average voltage. We will also examine difference waveform and work through an example verify the concept. Let's begin with an overview of RMS voltage. RMS stands for root mean square, which refers to the square root of the mean square of instantaneous value of a voltage signal. It is important to note RMS is specifically for time-varying sinusoidal complex waveform, and it's not applicable for DC circuits where the magnitude is constant. It's also known as the effective value because it allows us to compare AC and DC voltages in terms of their ability to produce the same heating effective power. For example, consider a 10-volt DC source connected to a 5-ohm load. The power generated is constant at 20 watts. However, with an AC source, the voltage fluctuates over time and we can directly use instantaneous values for power calculation. This is where the RMS value becomes essential, giving us an equivalent DC values for calculating power. A particular example is measuring city electricity. An AC voltmeter will show 220 volt RMS even though the voltage amplitude oscillates between 310 volts and minus 310 volts. This 220 is the effective value equivalent to DC voltage in terms of power. While if we measure the city's electricity with a DC voltmeter, it will show 0 because it displays the average of the sine function that we know is 0. Now let's look at the application of RMS voltage. RMS voltage plays a crucial role in various engineering and everyday scenarios because it provides an accurate measure of the power capacity of an AC signal. For example, in electronics engineering, RMS values are used to design and analyze circuits, including oscillators, amplifiers, and other components. RMS voltage ensures these devices operate effectively and safely. In heating applications such as electric stovetops or heaters, the RMS value helps determine the heating effect of AC currents passing through resistive elements. It's also significant in electric motors, where the RMS voltage contributes to calculating the mechanical power output. In lighting system, RMS voltage determines the brightness of the light produced by AC circuits. For example, the power of luminosity of the streetlights are often calculated using RMS values. For audio engineering, RMS voltage ensures that speakers, microphones, and amplifiers are designed to provide optimal sound quality. Finally, in telecommunication, RMS values are critical for designing and analyzing systems like telephone and data networks. Method of calculating RMS voltage. There are two primary methods for calculating RMS voltage, the graphical method and the analytical method. Both of them provide the effective or RMS value of a product, voltage or current. The graphical method is particularly used for non-sinusoidal waveforms or time-varying signals. It involves sampling the waveform at multiple points and calculating the RMS value. While an analytical method is a mathematical procedure for finding the effective or RMS value of any predicted voltage or current using calculus. In graphical method, there are four main steps. First, divide the waveform into equal intervals. In this picture, we just divide a half cycle, but you can do the full cycle if you want to. Second, Square the values of the voltage at each sample point. Pre-compute the average of these squared values. It means divides the total of these values by the total number of the points. And first, take the square root of this average to find the RMS value. Here is the example. In this image, you can see we divide this half cycle in 10 individual points. And then we find the voltage of each point and find the square of this voltage, then find the mean of them, and then take the square root of this value, and now we have the RMS voltage for this wave. The analytical method, on the other hand, is suitable for pure sinusoidal waveform and involves calculus. It defines the RMS voltage using an integral of the square of instantaneous values over a full cycle. For a sinusoidal waveform, that we have the equation right here, the formula simplifies to this. RMS voltage is equal to Vm, that is the maximum value that the waveform can have, divided by square root of 2, that is semi-equal to 0.7 times Vm, that we will see is called peak voltage. So basically, RMS voltage is equal to 0.7 times peak voltage. Let's now examine the relationship between RMS peak, peak-to-peak, and average voltage for periodic waveform. These relationships are fundamental in understanding the characteristics of alternating currents. Let's start with average voltage. For a periodic waveform, the area above the horizontal axis is positive, while the area below for horizontal axis is negative. The result is that the average or mean value of a symmetric alternating quantity over the full cycle is therefore zero. So, average or mean value for a symmetrical alternating quantity, such as a sine wave, is taken over one time period of only one half of a cycle. The method of calculating average voltage is similar to RMS voltage. The only difference is that the instantaneous values are not a squared function and do not make a square root. Here you can see the analytical methods of calculating average voltage, while we know that this half cycle is equal to pi, and the calculation is like this. And at the end we will have the average voltage is equals to 2 times Vm divided by pi, that it is known as V peak. So 2 times V peak divided by pi. We can also calculate average voltage by peak voltage, peak to peak voltage, and RMS voltage. We know that RMS voltage is equal to V peak divided by square root of 2. So RMS voltage times square root of 8 divided by pi is equal to average voltage. That means 0.9 times RMS voltage is equal to average voltage. We also said in the previous slide that peak voltage times 2 divided by pi is equal to average voltage, and as peak to peak voltage is twice as big of peak voltage, so peak to peak voltage divided by pi is equal to average voltage. Now peak voltage. Peak voltage is defined as the maximum value of voltage for any voltage waveform. The peak value measured from the reference axis 0 to the highest point of the waveform. We can calculate peak voltage by RMS voltage, peak-to-peak voltage, and average voltage. We know RMS voltage is equal to peak voltage divided by the square root of 2 in sine or cosine waves. So RMS voltage times the square root of 2 is equal to peak voltage. And we also know peak to peak is twice as big of peak voltage. So peak to peak voltage times 0.5 is equal to peak voltage. And we just calculate that average voltage is equal to peak voltage times 2 divided by pi. So average voltage times pi divided by 2 is equals to peak voltage. And now peak-to-peak voltage. Peak-to-peak voltage is the difference between positive peak voltage and negative peak voltage. For a sinusoidal waveform, peak-to-peak voltage is shown below figure. So we said that RMS voltage is equal to peak voltage divided by square root of 2. And we know that peak-to-peak is twice as big of peak voltage. So RMS voltage times the square root of 8 is equal to peak-to-peak voltage. And peak-to-peak voltage is also equals to 2 times peak voltage. And as we know that average voltage is equals to 2 times peak voltage divided by pi, and 2 times peak voltage is also equals to peak-to-peak voltage. So average voltage times pi is equals to peak-to-peak voltage. This is the end of the first part of this video. I hope you find it helpful. In the next part, we will examine the RMS voltage for different waveforms.